We're going to get started. I want to introduce the speaker. Peter Mazzo received the BS degree from Brandeis University in 2008 and the MS degree from Harvard in 2010. He just recently completed his PhD degree in computer science at Harvard with a doctoral thesis on graph databases, file systems, and provenance-aware systems, which he's going to tell us all about.
Well, just one of them.
Comes with a wealth of experience in corporate. He has performed multiple internships with companies such as Apple, HP Vertica, and Oracle. And starting in this March, he'll begin working as a research scientist at NetApp, where he'll explore the area of storage systems. Dr. Mazzo has been involved in academic activities throughout his career. As a result, he has co-authored numerous publications, including 2 patent applications from a summer internship at Apple and 1 from an internship at Oracle. Dr. Mazzo lives in Arlington, Massachusetts with his wife, who we are very proud to have here as an integral member of the Physics and Engineering department sitting right here. So this is with great pleasure that we welcome Dr. Peter Mazzo to the John U. Free Physics and Engineering Seminar Series.
All right, well, thank you for the introduction. All right, so yeah, thank you for coming. So my name is Peter Macko, and I'll talk about the research that I've done at Harvard at Oracle Labs. I'll talk about Llama, which is our system for efficiently analyzing graphs larger than memory. I've done this work with my collaborators Virendra Marathe, Daniel Margo, and Margot Seltzer. But before I start, let me just mention that even though a big part of this work was done at Oracle, this does not mean that Oracle will actually develop a product out of this. So basically, if you're going to make an Oracle purchasing decision based on this talk, you're out of luck. But let's get to the point. So graph structured data is everywhere, and a good example of these are social networks, in which you can model people as and pages as vertices and their relationships as edges. So Facebook does this, Google Plus does this, and so does about everybody else. For example, in this small part of a social network, you have, oops, that's not what I wanted to press. So you have vertices, 3 vertices in red. They are representing people, so they are my collaborators. Then you have several pages, and then you have edges. So Margot and Virendra are friends, so they have an undirected edge between them called friend, and Margot likes baking, so there's a directed edge from Margot to baking. And these graphs change. So for example, as Daniel develops his interest in baking, he would like to click the like button on a Facebook page called baking, and what Facebook would do in the background is will add an edge going from vertex Daniel to vertex baking. Similarly, if Virendra gets fed up with traveling, then he will unlike the page called traveling, and Facebook will remove the edge between Virendra and traveling. So I'm a little bit oversimplifying, but overall this is the gist of what's happening. And there are many reasons why people like to study these graphs. So for example, Facebook analyzes these kind of graphs to give you your friend recommendations. LinkedIn uses these kind of graphs to suggest which groups you would like to join. And there's a lot of research, especially in the sociology, who analyze these graphs to study things like user influence or like rumor spreading. Kind of the idea is that if Margot starts a rumor, then maybe her closest friends will be the first one to hear, and there's a lot of algorithms that can be modeled at. And this is just one example of a social network. Another example is the Twitter network, in which case you have nodes representing people and directed relationships showing who follows whom on their Twitter feeds. And as you might imagine, these graphs can be very large. So just think, Facebook has, I think last time I checked, 1 billion nodes and hundreds of billions of edges. Twitter is on the order of many millions of nodes and billions of edges. And these graphs are much larger than would fit in the memory of a single computer. So, and it's not just social networks. You can find graphs everywhere. In biology, they are used to study protein-to-protein interactions. In road networks, they are used to study maps. And this data grow very quickly. You get every minute almost 300,000 new tweets, 26,000 Yelp reviews, and more than 3 million Facebook likes, all of which you can model as edges in a graph. So this presents some very interesting challenges for us. We need to be able to analyze large graphs quickly to keep up with the incoming updates. We need to efficiently handle the incremental ingest, and we also would like to provide the ability to focus just on the recent changes, which we can do by the sliding window abstraction, which I probably wouldn't have time to talk about in this talk. My focus in our project is single machine performance. So more specifically, my goal is to provide fast analytic performance in the presence of updates or in a different terminology, mutations, by exploiting read-optimized data structures and making them mutable with minimal overhead. And then the second goal is to process large graphs by exploiting persistent storage, especially SSDs. And the idea is to do that without paying the penalty for being able to compute on graphs larger than memory. So I said my focus is single machine performance, but and as much as it is cool to process all of the Twitter graph on a laptop, then an interesting application of this for people who do things more like Facebook scale graphs is that once you have systems that can process on graphs larger than memory, then you can build better distributed systems to process even larger graphs. So the following table summarizes the related work in the area. So these are all different systems or categories of systems that people built to demonstrate as a proof of concept. And you can divide them into several categories. So you can have main memory only systems on the left, which require that all of your data fits in RAM. So in reality, you are fairly constrained in how large data you can process. And there's the out-of-core systems on the right that allow you to process systems larger than RAM. Then for each of those categories, you can further divide them up on whether they support updates or whether they are read-only, meaning that if you have any updates, you have to shut down your system, reload the data, and start from the beginning. So the interesting thing is that so this corner is the fastest corner by far, because each time you add features, like you add updates, that's going to cost you something even if you are not using updates. Or if you add larger out-of-core, or larger than RAM analytics, you're going to pay for it even if you are not going to use it. The problem is that we would like to be as fast as these fastest systems, but we want the features we want these features, because if you have updates, and these graphs change pretty quickly. You want to just update your data and go finish running your computations. You don't want to shut down and spend again several minutes or half an hour, however long it takes to reload the data. And then as data grows quickly, you will also like to be able to compute on large data that doesn't fit just on your computer. So these are all desirable features, but they cost. So the goal is, can we provide them without costing anything? So let me tell you how do we get there in this talk. So we started with the best representation in these read-only, main memory-only systems. Then we added mutations with very small overhead. Then we made it persistent with, again, very small overhead. And we ended up in a system that we, for some reason, called Llama, which actually stands for Link Node Analytics Using Large Multi-Version Arrays. So I tried really hard to make it be Llama, so forgive me for that. I already talked to some people before that. For some reason, different projects in our groups have different animal names. We have goats, we have alpacas, we have sheep. So So first, let me tell you about CSR, which is kind of the gold standard in graph analytics. That's where we started. Then next, I'll tell you how we made it mutable. Then we made it persistent, which means using like an SSD or not just your RAM. Then I'll mention some other features of our system, but without really explaining them, because we probably wouldn't have the time. And then I will show some performance numbers and conclude. Before I tell you what CSR is, let me tell you why we chose CSR. So you can break down the approaches to storing graphs into 3 categories. The first is called CSR, the second is adjacency list in separate arrays, and the third one is compressed sparse bitmaps. This is running breadth first search, which is a common thing people do, which is common building block of many algorithms. And you can see that CSR is by far the fastest. The problem is also CSR is the only one that doesn't support updates, and is also the only one that that doesn't naturally work with out-of-core computation, which are the 2 desirable features we would like to add. But we care about performance, so we're starting with CSR and see where we get. So before telling you what CSR is, so let me just give you a little bit of a background, and then hopefully you'll get on the same page. So a graph can be represented as a square n-by-n matrix. If you have a value at position ij, I is the row, j is the column, then 0 means no edge, or I'll just leave it blank in my notation, or 1, which is a directed, 1 means there's a directed edge going from I to j. If you have an edge going in both directions, then you also add 1 to position ji. The rows correspond to the outgoing edges. So for example, row 0 corresponds to the vertex 0, and there's 1 at position 1, which means that there's an edge going from 0 to 1. For row 1 corresponds to vertex 1, so there's 1 at positions 1 and 0 and 2, which means there's an edge going to 0 and an edge going to 2. And likewise for row 2. Columns correspond to the incoming edges. So you can see there are 2 incoming edges to vertex 0, because there are 2 ones in this column at positions 1 and 2. You can see that there is an edge from 1 to 0 and from 2 to 0. Column 1 corresponds to vertex 1, column 2 corresponds to vertex 2. So this is the very commonly used matrix notation. We usually don't represent graphs like this on a computer, but we like to. But it's the theoretical foundation for graphs. And in most real-world cases, the matrix is very sparse for many graphs, meaning that like almost all elements are zeros. And we are going to leverage this information when we talk about CSR. So now let's convert this square matrix into a simple row-wise implementation. So we're going to have a vertex table and an edge table. The edge table is going to contain just all the rows stored back to back in one consecutive piece of memory. Each of these this square is just some number of bytes. This is all contiguous piece of memory, and then we have a vertex table which contains pointers. They are about 8 bytes each to where each of the rows start in this edge table. So for example, if you would like to determine which edges go out of vertex 2, then you can just find the element 2 in the vertex table, then you follow the pointer and you see there's 1 in position 0, 1 in position 2, so which corresponds against to the graph. Now, so I told you that the matrix will be sparse, meaning mostly zeros. That means edge table is basically just a matrix in a little bit different order. So there's also going to be mostly zeros. So we are going to use this to now compress this to create the compressed sparse row representation, or CSR, which is the thing that I finally wanted you to explain. And the key idea is that we only go to store the indexes of non-zero elements, leaving out the large chunks of zeros in between. So again, we're going to have a vertex table and an edge table. And so let's start. So for row 0, there's only one non-zero element at position 1. So we're going to just write 1 just as a number in the edge table. And then a vertex table is again going to be a point to say 0th element in here. So that's where the row starts. Then for the row 1, then can write 0 and 2 because the only non-zero elements are at position 0 and 2, and likewise for row 2. So that gives us CSR, and then at the end we end up with, you add one more element to the vertex table in gray that I put here, which is the number of elements in the edge table. And now you can observe that each of these rows, so here they are like each same width, but now they have there's 2 elements long, 2 elements long. So I need to figure out how long they are. And you can do that just by subtracting, taking the difference from the 2 consecutive elements in the vertex table. So for this last guy, you subtract 5 minus 3, that means there are 2 elements here. Now observe that in this representation, compressed row is the same as adjacency list, which is the list of the other endpoints. So for example, again for vertex 2, we follow the arrow, and you see there are 0 and 2. The vertex table, to recover this table on the top, is the map of the node ID to where the adjacency list starts. The edge table on the bottom is adjacency lists in a single array, and the end of adjacency list you can determine from the next vertex record. So this is very briefly CSR, and it's the gold standard in graph analytics. A lot of people do this because it's compact, because you store things consecutively. You end up with so first of all, you eliminate all those zeros, then you store these things compactly, which eliminates a lot of malloc overheads, if you know what I mean by that. If not, that's okay. Then because things are compactly and stored in the vertex ID order, then you end up with a good cache behavior, which has very good implications on performance. The problem this is read-only. If you want to insert an edge, you'll have to shift basically all of your edge table to make a space for one or however many edges you are inserting at the right place. And it also assumes that the whole thing fits in memory, which we would like to, both of these are a problem, we would like to remove these assumptions. So let's start at removing the assumption that this is read-only. So instead of modifying CSR directly, which I told you we're not going to do, we are going to treat this as a multi-snapshot CSR thing, whatever that means. So this is our initial graph here at the bottom. We're going to call snapshot 0 CSR, and we are going to record all the updates here on the top in one of the other representations that's actually optimized for writes. And at some point, whether it's some number of seconds, minutes, or some number of added edges, you decide to create another snapshot, and you will move the edges to the new snapshot. You'll create another version of the vertex table that points to the new edges from the correct elements of the vertex table, and the rest of them then it's kind of hard to see, will point to the previous snapshot. Now let's say you get 4 more edges, 2 to vertex 1, 2 to vertex 2, and at some point you create another snapshot, you move the edges, and you create another version of the vertex table. So instead of modifying a CSR directly, you are going to create another snapshot, and together with the other CSRs, it will contain the whole graph at a given time. Now, because we have a multi-snapshot approach, we get multi-version access for free. So what I mean by that is, for example, you can start a long-running clustering operation or whatever you want on an old version of the data while there are more updates are coming in, while you can compute, for example, Google PageRank from Google on one of the newer versions of the data, while you are getting more updates at the same time. So now I'll not talk about the writable graph representation because that's not really novel. Let me focus in the rest of the talk on this multi-snapshot CSR. So notice that we have one edge table per snapshot, and then also the way I drew it, there's one vertex table per snapshot. But if you actually did this, then this one vertex table per snapshot, you will run out of memory pretty quickly. For the Twitter graph, which just says who follows whom, its vertex table is about 1 gigabyte. So if you do this every minute or so, you get your 1 gigabyte per minute. You'll quickly eat up your memory. So we're not going to do that. Instead, we are going to use a multi-version vertex table using a technique called copy and write. So what that means is that instead of storing vertex table as one big chunk, we are going to break it up into small equal-sized chunks and store them have them on multiple pages. So at this point we have just 4 elements and I'm putting 2 per page. In reality you'll have like 256 or 512 or more per page. And then on the top we're going to put an indirection table or an indirection array that's going to then compose the logical vertex table out of these chunks. Now when you want to create a new snapshot, you first copy the indirection table. At this point, snapshot 0 and snapshot 1 contain exactly the same data because the indirection tables are the same. Now, if let's say there are 2 new edges coming to vertex 0, so we need to modify v0, but and we're going to do that by first copying the page that contains v0 and updating the indirection table accordingly, and then finally we can update v0 to point to the new edges. And now that you've done this, so this contains all the new information, but notice that page 1 is shared by both snapshots. So we're actually saving memory because we are only copying the smallest numbers of pages that we need to. So for now, I've been using the V0, V1, V2. Now let me tell you what each of these are. So we're storing 3 numbers. We pack them in 16 bytes. The first is the snapshot or edge table ID because we are going to point to one of the edge tables, so we need to figure out to which edge table we are pointing. Then the second number is the index in the edge table, so where in the edge table, and the last number is how many edges are at that position. Now this is finally a complete example of this graph stored in one snapshot of Llama. So we have vertex table, which have indirection arrays, table the different pages, and finally the edges. And again, looking at vertex 2, you can see that you can go for the indirection array. You find v2 in this page. Then you can see that it points to edge table 0. That's this guy. Position 3, so that's here, and there are 2 elements. So and it's 0 and 2. So you know there's an edge to 0, there's an edge to 2. Now let's add 2 edges to vertex 0 and remove an edge from vertex 1. So let's see how we do this. So first you create another snapshot. You do that by again duplicating the indirection table. And now snapshot 0, snapshot 1 are identical. Now we're going to process the vertices in the ID order. And this is actually important to preserve some of the good properties of CSR. So the first one is 0. So we're going to add 2 edges to that. But to do that, we need to first modify v0. So we just copy to the corresponding page. And then we're going to write the new edges to the edge table and change this entry to point to the new edges. And then we're going to finish it with a pointer to the rest of the edges. So this contains the same information. So snapshot ID 0, position 0, there's one more edge there. Normally, when you are done, when you only point to the last fragment of edges, then you put a null pointer at the end, meaning that this is the end. But you don't have to do that in snapshot 0 because that's the lowest snapshot by definition because there's nothing going before 0. So you can omit that and save space. Now let's delete an edge from v1. So we already copied the page with v1, so we can modify it directly. And we are going to handle deletes by just rewriting the complete adjacency list here. So now the only remaining edge is this guy from 1 to 2. So you just write 2 here and you finish it with the null pointer, meaning that this is the end. So now if you want to figure out what are the edges going out of v1, you just find 2 and that's it. If you want the old version, you go for snapshot 0 and you figure out what is the old version. So you still can see, you can also have the multi-version access while implementing these changes. So now this is finally the complete example of a 2 snapshot Llama. Hope it makes at least a little bit of a sense. Are there any questions at this point? All right, so let's limit now. All right.
When you're updating the edges, where are you reading data from RAM?
So
The data that you're using to update.
So data that I'm using, good question. So it depends on your application. So when I'm just computing things on graphs on my computer, I usually have data stored somewhere on disk. I just read. Usually data comes in the form of vertex pairs. So the source vertex, target vertex. If you are somebody like Facebook, it actually comes usually over the network because somebody decides to click a link or decides to click like or decides to delete and unlike something. So it will come as an update over the network.
So the other thing is, so I assume when you were talking about persistent data versus data that you're just reading from one, right?
So at this point we are still in RAM. We're going to SSD in the next few slides.
Right.
Okay, so all right. So now let's talk about making this persistent, meaning using anything other than RAM. But first, before I tell you what to do, let me first tell you what not to do. So this is the result of running CPU profiler on Graphql and Extreme, which are the two main competitors to our system. So what I did, I took the Twitter graph and I ran a PageRank on it, which in the context of a social network measures users' influence. And so this is a CPU-bound computation, first of all, which might be a little bit counterintuitive because it's larger than RAM, but the bottleneck is the CPU, not your disk, which actually a lot of people might find surprising. And so, the CPU profiler then so tells you where is the CPU spending the time, and so I categorize this in these broad categories, and you can see the percentage of useful work, which is this guys in red, is only 12 to 25%. That's the thing computing PageRank. The rest of the time, the CPU is spending on loading pages from disk, writing temporary data back, shuffling data around, and and basically a little lock-in synchronization, that kind of stuff. So basically stuff that's not actually useful work. This is this is what I meant by when you have even if you have features that you're not using them, you still have to spend the time on supporting those features. So this is not the not useful work that we are trying to get rid of. If we like to be competitive with the in-memory only systems, our percentage of useful work needs to be near 100%, because if you are an in-memory only system that assumes everything is running already, it's not going to spend any time doing all these extra activities. So let me tell you how we got there. So first of all, it's necessary that the in-memory format is the same as the on-disk format, so that we don't have to spend any time transforming data between how it looks on the disk versus how it looks in memory. The only exception to this rule is a few small places like the indirection arrays and the vertex tail, which is the small thing on the top that we store as in-memory addresses in memory versus on-disk addresses when we are on disk. But other than that, everything is the same. What this allows us to do is we can use memory mapping to delegate the buffer management to the operating system instead of re-implementing it ourselves. This means no overhead due to things like pinning pages in memory, no overhead due to checking whether a part of the graph is present before accessing it, and overhead to do things like eviction scheme figure out which things to evict next when you need to make space to load up another part of the graph for analysis. The result of this, if the graph is in memory, and once the operating system loads in all of the graph, then we compute on it as fast as if it was a dedicated in-memory solution. So ideally, we would like just to map everything. The bad truth is that it works in our case, but there are many bad. But you can misuse a map pretty badly, because by using memory mapping, you give up the control over what part of the graph is in memory at any given time, which means that if the operating system and you disagree what should go to the memory next, you're going to risk some significant performance problems. You can also end up with a lot of wasted I/O, which means, for example, the operating system decides to load some 4 kilobyte chunk if we use only 16 bytes of it and throw out the rest. So we end up with a very inefficient system. The good news is that by preserving all the ordering properties of CSR, even in this multi-snapshot approach, we actually can avoid suffering from most of these problems. So in practice for us, on the many analytic workloads that attach a large-ish, not large, or kind of like some significant part of the graph, we perform just as well as if we did all these things ourselves. And the other half of the story is that the other people in our group, so Daniel Margo, who is one of my co-authors on this paper that I'm talking about, he's working on K-tree embeddings, which to resolve some of these problems. And then we have a group of undergrads, Albert, David, and Yaniv, who are working on prefetching using M-Advice. And that's well, the combination of these that they extend the good performance of Llama to other types of workloads, even the ones that I would never guess we would normally be able to support very efficiently. So now let me talk about just some other features of Llama that I'm not going to talk about now unless someone is really interested. And you can ask me at the end of the talk. I can bore you with all the gory details until you fall asleep. So graphs are only so useful as long as okay, let me say differently. So the graphs are useful only like so much, and but if you add properties, then they make them much more useful. Properties meaning like a name of a person, date of birth, that kind of name of a page, what type of edge it is, that kind of stuff. So we implement multi-versioned properties similarly to that multi-versioned graph structure. We can furthermore maintain incoming edges in addition to outgoing edges. So for example, if you are on Twitter, outgoing edges allow you to ask who do I follow? Incoming edges say who are my followers? You can delete edges in a different way that I mentioned that saves memory but causes some performance issues. For delete heavy workloads, we can create delete vertices. We have the in-memory write optimized graph store. We can delete all versions of a vertex table that we don't need. We can merge snapshots because, as I mentioned, you create new snapshots like every maybe few minutes, but then you end up with like 60 times 24 times whatever. If you did every minute, you get some 3-digit, 4-digit number of snapshots per day. That's not sustainable. So you can merge snapshot periodically. And then finally, we can just focus on the recent changes using a sliding window over a time series of edges, which, again, if you are interested in any of these, you can ask me later. So now, before I end, let me show you some performance numbers. So first, let's figure out what do we want to learn. So first of all, my first question is, how does Llama compare to the existing solutions? So, and there are two things we'll be looking at. The out-of-core performance, which means larger than memory, and then in-memory performance. And then there I'm especially interested in comparison to the read-only CSR, which is where we started. Then the next is the cost of multi-version access, like when you have more than one snapshot, how does it look? And then we'll see how the performance of Llama scales in the number of CPU cores and in the graph size. I'll run most of the benchmarks on a Twitter graph. And then that's the vertices are people and edges are the follows relationships. I'm going to run 3 experiments for the most part. The PageRank, which normally is used for ranking web pages, but in the context of a social network, you can be measured. It actually is a pretty good indicator of user influence. Breadth first search is a building block of many algorithms. In a social network, it means like determines your friends, friends of friends, and friends of friends of friends. Then in the triangle counting is a building block of many other algorithms, a lot of importance and centrality metrics, but by itself it measures how well the network is interconnected. So the Twitter graph has about 42 million nodes and 1.5 billion edges, and I listed for all but one experiment. The last one I'm going to run on RMed graphs, which are synthetically generated from the Graph 500 benchmark. I'm going to run this on two computers on a commodity platform, which is a dual-core Intel Core kind of CPU, 8 gigabytes of RAM with SSD. That's kind of fancy, but not too fancy. That's the kind of stuff you can find, you can normally get your hands on. And then a big memory platform, which is a 64-core multiprocessor with 256 gigabytes of RAM. And I'll use this to illustrate the 2 points, the out-of-core and in-memory performance. So let's start with out-of-core performance. So I'm going to compare Llama to GraphQL and Extreme, which I mentioned before in one of the previous slides. And we have three charts, PageRank, BFS, and triangle counting. The vertical axis is how long it takes to compute it in seconds. So this is on the commodity platform, and on which the Twitter graph is 50% larger than the memory. And Llama performs significantly better than all of the competing systems, primarily because the percentage of useful work in Llama is around 98%. Now, moving on to in-memory performance, I'm adding 2 more bars in black. Now I'm on the big memory platform, and the 2 new systems are the read-only CSR, which is where we started, and the GraphLab, which is another system. So again, Llama performs better than GraphQL and Extreme, mostly due to also CPU scaling, the number of CPUs, which I'll show you later, but also due to the percentage of useful work. GraphLab actually has a pretty good scaling, but has only 33% useful work, so it doesn't perform as well. And you can see that we are performing on par with read-only CSR, just maybe like few percent at most slower than we pay for these features, just a small cost. Now this is the cost of the multi-version access. This is now, I'm back to out-of-core performance, so meaning 50% larger than RAM. And now showing the loading time, PageRank, and the BFS. And a very narrow snapshots from 1 to 11 on the horizontal axis. The vertical axis is the time in seconds. Red is Llama, black is GraphQL for reference. So the way I did this, for all but 2 or more snapshots, I loaded 80% of the graph in snapshot 0 and evenly distributed the rest of the edges in the remaining snapshots, modeling different frequencies of updates. So the loading time, and everything else. So Llama is fastest when there's only thing in one snapshot, which is the best case, and then loading time gets worse. And there's this little tip that I can explain to you later if you are really interested why. There's actually good reason for that. But anyways, the interesting part is that if you look at these guys, so this is the curve for PageRank and BFS, so the actual graph computation. There's the biggest slowdown from 1 to 2 snapshots, which is less than 10%. Here is more like 5%. And then with each more snapshot, it flattens out, so each new snapshot costs you less and less progressively. So which means we can support potentially large number of snapshots without really sacrificing much of a performance. I ran this up to 200 snapshots, doesn't get that much worse. This is actually the most interesting part because the most slowdown is right here at the beginning. Now, going back to in-memory numbers, let me show you the scaling plot. This is for PageRank, the other ones look about the same. This is comparing the different systems on a log graph, so log time, log number of CPU cores, and Llama is in red, Llama 11 is Llama, in which we loaded the data into 11 snapshots, and read-only CSR is green. And if you'll notice that, so this is actually Llama 11, and green. It's they scale the same way, basically, which is the best possible behavior that we can get, because read-only CSR is where we started. So we can't get any better than that. It scales on par with GraphLab, which is the other in-memory system, but it's overall a little faster because the percentage of useful work is much higher. And you can see that that Extreme and GraphQL level of around 4 and don't improve anymore. This is because they are hitting some inefficiencies inside the Linux virtual memory system. Now, the final set of 3 plots I'll show you is scaling in the graph size. So this is, again, this is now going out of core. I'm using this time the RMAT, synthetically generated graphs. The horizontal axis is scale, which is the log2 of number of nodes. So we are going from 2 to the 25 to 2 to the 29 nodes. The vertical axis is log, is time in seconds. And the scale 25, this is about 1x memory size, this is about 9 times memory size. And this is again Llama and Llama 11 in red and dark red compared to GraphQL and Extreme. And the scaling, you can see the scaling is actually, they all scale the same. They are all basically lines in this log-log plot. And in all cases, we are beating or at least matching the state of the art. So, in conclusion, so I presented about, at least briefly presented about Llama, which is a graph analytics system for graphs larger than memory that supports incremental ingest and updates. It's as fast as dedicated in-memory systems where the graph fits in memory. It is efficient on graphs larger than memory, and we achieve this using modified compressed Sparse representation in this. I didn't use this word before, but it's actually called the log merge architecture with multiple read-optimized snapshots, and making sure that on this format and in-memory formats are the same, and using memory mapping. All right, thank you, and I'll take any more questions.
How does your do you guys do the page ranking algorithm as well with Llama?
Yes, actually, the numbers I will most of the numbers I was showing is page rank.
How do you guys handle like any nodes that don't connect to any other ones? In the sparse representation.
Okay, so the typical PageRank implementation that also we are using is that you iterate over all nodes in the ID order. So you go basically if you have n nodes, then you go for then you write parallel 4 from from I0 to n, and then you push your weight to all the outgoing edges. So the graph itself actually, the algorithm itself doesn't actually depend much on the graph topology. So it's completely independent in that sense.
So Llama is owned by Oracle?
Good question. So Oracle owns the patent on Llama, but it was done. So I did this half at Harvard and half at Oracle. So who owns it? I don't know. It's actually there's a proprietary Oracle version inside Oracle Labs, and there is a constrained open source version on GitHub. And that's kind of what we agreed as the compromise for the ownership.
What's your simple explanation for how multiple snapshot improve performance?
So multiple.
Follow-up question to that is, what do we lose in data quality by letting the OS take over?
So snapshots don't improve performance. Snapshots decrease performance, but they don't decrease it as much as if we use any other approach to mutating data.
You showed some graph where most snapshot you're going down, kind of thing, right?
Yeah, you can only refer back in time. You can't reference the future, okay. Right? So you always reference only the older snapshot. So I mean. Let's see. Okay, so I don't. So this is. So I wonder if this answers your question.
Yeah, that's right. So the other thing, when you relinquish control to the OS,
okay.
sometimes you're picking up 4 bytes out of 12 or whatever.
Yeah.
Any cost you paying in data quality?
So you don't pay the cost in data quality. It's all about performance.
Okay.
So I can actually. Okay. So basically, okay. So let's see. So I can go to the so there are the 4 issues in more detail. So when the data, so normally I say we give out the control of the data is brought in memory. So it turns out that the operating system is pretty good in figuring out when you access data sequentially, and if once it detects that, it knows you are going in order, so it knows what to give you next, right? The nice thing about CSR, everything is stored in order. So if you process the graph in the vertex ID order, or at least at least there are some kind of if you include enough sorts in between that you actually do as much as in order as you can, the OS scanner will pick it up and do the right thing.
In order, even when you are core?
Yes. So PageRank, for example, that's the simplest example, because you go from vertex 0 to vertex n. And in CSR, it stores all this information consecutively in that source ID order. So it'll be reading basically your vertex table from left to right, your edge table from left to right. For things like BFS, there are actually several ways to do this. We have actually 2 implementations. One is meant for in-memory, which is not very efficient out of core because it assumes. Because it doesn't really sort ways, but then there's also out-of-core implementation for BFS, where it just makes multiple scans over the graph, and in that case, just make multiple iterations over it, always reading from left to right. And then when you have multiple snapshots, so that was for one snapshot. When you have multiple snapshots, because we preserve these ordering properties within all snapshots, then you don't get this sort of sequential scan anymore. So you don't get just left to right, but you get left to right on all of the snapshots, which you get several. If you have n snapshots, you will have n+1 reads from left to right, which the SSD is actually very good at. But on a hard drive, the performance is going it's going to take forever, but an SSD is going to be very fast. Any more questions?
Over a general question. Is this fundamental research for the sake of the research itself, or does Oracle have a more practical application a need that they're trying to solve?
So,
kind of a follow-up to that connected is, how do you balance technological advance as compared to theoretical algorithmic advance? So as processors get faster, memory gets cheaper, you can win that way as well. So does this have a specific application that Oracle is trying to solve that can't solve it?
So I remind you of the disclaimer. This is only intended to, whatever. So disclaimer: don't make any purchasing decisions based on this. But that being said, Oracle is starting to ship a graph product. So they have 2 graph products. It started with there's the network data NDM network data model, which shipping for a while. This mostly does maps and geospatial stuff. And since last year they are shipping PGX. I have those letters in correct order, and that's a more generic graph product. Currently, it doesn't support updates. So this was one of the ways of Oracle, and so basically they're like, okay, what are the different ways we can support updates, and then they'll eventually pick something. But again, I can't make promises to make the whole product, right? I'm just saying, okay. So your second question. So it came out of a practical need. Somebody was like, okay, well, we need to make CSR mutable. So first of all, can we stay with CSR? And if so, can we make it mutable? Then I was like, okay, let me give it a try. And then your next follow-up, which was the computers getting faster and RAM getting cheaper. So the question is, yes, you can win that way, but at what cost? And at this point, I can at this point go ahead and you can build for $40,000 big enough computer that will fit a lot of this stuff in RAM, but the question is at what cost? Because the data grows really quickly. Facebook, and this is actually a 2-year-old number, 3.2 million likes, which meaning new edges per second. Per minute. So you know, how long, right? How big of a computer do you need to provision for a year, right? So at some point the data just grows too fast. And since nobody, well, and then before anybody comes with another question for the CPU. So it turns out, yeah, I mean the CPU is actually not getting any faster anymore. Now a lot of we just get more of them. And then the other thing is the I/O is not really getting any faster. I mean, there are people working on new I/O technologies, but you know, we'll see. Only God knows when they'll come into practice. Any more questions? Anybody have any more questions?